Any questions about where we're at so far? Anybody would like to ask anything? Okay, so then I'll ask you a question. Where is error in a Bernoulli distribution? Where's the error term?
I know.
Well, there's two ways of thinking about it. I'm going to give you the way on the slides, and you can give you the distribution way sometimes. I look at error. You think of error in a regular regression model is how far you were away from the predicted observation, right? So here, I think of error as representing how far a probability is. When you make a prediction, it's a probability now, right? How far that probability is away from 0 or away from 1. I think of it that way. That's sort of how far off in the prediction is. It's sort of, you think about it, if you're predicting somebody's probability of answering an item with a 1 as 1.0, you're basically saying there's no uncertainty at all in your prediction. And the same thing if you're saying that probability of the answered item with a 1 is 0, there's no uncertainty in that prediction, right? There's no error to it. Likewise, a probability prediction of 0.5, it's like saying you have no idea if the answer correct or incorrect. So that's sort of the my very non-technical description of what error kind of looks like in a model. But Lisa has a better description that's much more technical.
Oh, yeah, because that's what I'm known for, super technical. No, so what sometimes confuses people is the lack of E. It looks like it means that we're assuming the prediction is perfect, and that's not the case. It's not that it's perfect, it's that once we know what your predicted probability is, we know what the variance around that has to be. So if you're predicted to have a probability of 0.8, it's 0.8 times 0.2, the end. If you're predicted to have a probability of 0.9, it's 0.9 times 0.1, the end. So it's the symbolism is that the variance is known based on the predicted mean, not that there isn't any. And so there is still error in the prediction, of course. We just don't have to worry about treating it as a separate parameter with constant variance, which, if you think about it, is crazy to the extent that you have an item response that has some kind of boundary, like 0 to 1 in this case, or ordinal data. The variance has to shrink the closer you get to the endpoints because there's nowhere for it to go. So to me, the assumption of, is it continuous enough to be able to use a regression type model? It's like, well, it's not just the normality part, it's the constant variance part, because if you assume the variance is constant when it's not, that means sometimes you're going to assume too much error and sometimes it's going to be too little because you're assuming something that's towards the middle.
I thought you were going to go a different direction. Sometimes, in this linear predictor right here, this looks more like a regression model where you would expect to have an error term to it. When predicting a logit, you see this more in the multi-level literature. Like if this is a level 1 type variable, sometimes if you need to form an interclass correlation, you need a variance at the level 1 to be able to do that. Oftentimes people will say this maps onto a logistic distribution. And the logistic distribution does have a variance with a sort of a scaling constant. And so for the variance itself is not identified, we sort of fix it to 1, but the scaling constant still maintained. So sometimes, if you follow Lisa's materials, you'll see her talk about something called pi squared over 3. It seems oddly specific, why is it pi squared over 3, right? But that is where this comes from. If you look up the logistic distribution in Wikipedia or something along those lines, you'll see a pi squared over 3 times a constant for the variance. We put a 1 as the constant, and the pi square over 3 comes there. But that's like saying when predicting a logit, the error would be logistic distributed, which is its own weird distribution. But that's in the weeds. You don't see that in measurement models, at least that I'm aware of.
Oh, yeah, you do.
You see pi squared over 3 in measurement models? I didn't. Where do you see the pi square over 3?
So have you heard of, sometimes in notation it's like y star as the underlying latent variable?
Yes.
It's like, no. We don't have a binary response. What we have underneath it is the continuous response that really should be there, except we only have the 0-1 version. And the variance of the pretend underlying continuous response is 3.29, which is pi squared over 3. And then someone else is like, nuh-uh, the pretend underlying distribution is normal, not logistic, and the variance is 1. And those map onto logit versus probit respectively. But we don't have the actual underlying distribution, or we would have used it. So there's no way to know if you're right.
So all that nuance is not on slides, so you can just forget it until you absolutely need it. But the bigger picture is it's constant. Like the variance is known in this sense. Whether you're on the Bernoulli side, which is the variance is p times 1 minus p, or you're on the logit side where we assume a logistic outcome, a variance that follows a logistic distribution. You're right about that.
Yeah, we do. So I do cover this in the case of observed predictors in my generalized modeling class, and I also cover it in terms of latent variables in my structural equation modeling class. So if anyone wants more on that, that's where you can find those things.
LisaHoffman.com.
That was a birthday present, actually, that he bought me my own domain as a birthday present.
I bought a few piles of variance.
He bought piles of variance, which is my book's domain as well, because that's what nerds do for each other on their birthdays. They buy domains.
Makes a lovely birthday present. Maybe not anniversary, but birthday. All right. So if we now, just like in the previous example where we went from regression to confirmatory factor analysis, if we go from logistic regression, now we end up with latent variables. We're into a world where we're effectively in item response theory or item factor analysis. So similar to the previous example, if we did not observe theta, we would still need the same specifics for sets of items. We'd need at least 3 items to identify the scale. We'd have to figure out the mean, we have to figure out the variance, we have to set the scale for identification. But the measurement model for an item itself, for the response to an item, conditional on the latent variable, looks the same as the other slide, with the exception of that I've substitute the symbols that we use in the latent variables for the symbols that we use in logistic regression. So again, mu is the item intercept, representing the expected logit of a correct response when theta is 0. And lambda, I, is now the factor loading, or the term that we often use it in psychometrics is discrimination parameter, right? Which is honestly not the best term to tell a discriminant. So we have a parameter about discrimination that doesn't seem like the wording of it seems a little harsh, but technically speaking, the bigger this parameter is, the bigger the expected prediction of the correct response is between people of a high or a low theta, right? So but it functions the same. Sometimes we call it a factor loading, sometimes we call it discrimination. So here, again, we map those 2 parameterizations. Sometimes we call this item factor analysis, this parameterization. The key that I like to think about is this is something we call slope-intercept parameterization, because we have a slope, lambda, and we have a intercept, mu, for it. Turns out sometimes in item factor analysis, depending on the software you use, we swap out mu for negative mu, which we then call a threshold. And that relates to when Lisa was talking about this plausible underlying continuous term. There's a connection to that in it. Technically speaking, item factor analysis and item response theory are roughly the same, but when we talk about item response theory, we're often in a different type of parameterization. It's no longer a slope intercept, but it's something that we call discrimination difficulty, right? Often, I don't have it here, but basically we're going to take a little bit different take on things. We're just going to call, instead of calling the slope or the discrimination parameter lambda, we could call it A, and then we would change, instead of having an intercept, we might form a parameter B, which we call difficulty, that is -1 times the ratio of the intercept to the slope or the discrimination parameter itself. And I'm remiss in my slides because really what I wanted to show you, I need to draw. So what this really works out to be, the probability that y for person item equals 1, given theta for the person, it typically looks like this. A for the item times theta for the person minus B for the item.
I have it on my picture.
Okay, well I'm going to put it here too. A for the item, theta for the person, minus B for the item. So here, this is the form of a 2-parameter item response model, unidimensional. There's one trait right here. This is your item discrimination. This is your item difficulty. You may often find this when you talk about item response theory, whereas you might see this form, the linear form here, when you talk about item factor analysis. But they are cousins, parallel to each other, equivalent in many cases. Not so much in the Bayes case, but depends on what prior distributions you put on. But from a measurement model perspective, they are roughly equivalent. And now this is Lisa's slide.
I wanted to say my slide in, so forgive me for the interruption here. But this is something that at least my students have a hard time with because they see all these different versions and it's like, is this the same model or is this not the same model? And the answer is yes, it is the same model. So depending on your software, how many of you use M+, for instance, to do analyses? Anybody? A couple of people? So if you fit these models in M+, you get something called a threshold.
Or Levon also.
Levon gives you thresholds as well. And a threshold is an intercept times -1. So in terms of like the location of the item, you might get an intercept, you might get a threshold, or you might get a B difficulty value. And so I wanted to show basically how these things map onto each other. These formulas hold if theta has a mean of 0 and a variance of 1. There's extra stuff that goes into them if they don't. But basically, each of these is tied to something being 0, but what that 0 is tied to is different. So on the x-axis, there is theta as our latent variable, and on the y-axis is the probability of a 1 response, where 0.5 on the probability marker is the same thing as a logit or a probit of 0. So what a difficulty value gives you is the x value at y equals 0. What an intercept tells you is the y value at x equals 0. So they're just like opposite of each other. And so I have it marked on here like where the difficulty point is as the blue part, and then where the intercept is as the red part on the top of that. And then you take the intercept and multiply by -1, and that gets you to your threshold. So what can be tricky, I think, about learning these models and actually putting them into practice is figuring out what exactly you get back as your parameters. The A part is usually easier because A is the same thing as a factor loading if you're using a standardized latent variable. Otherwise, it's the loading divided by the variance. There's an extra thing in there. I don't remember it off the top of my head, but there's a conversion. So.
And when she says y at 0, she's saying logit of y. So otherwise, probability of y at 0.5.
Yeah, probability of 0.5 is logit or probit of 0. So, and probit is OJEF.
Yeah, and if we go with y probability of 0.5 is 0, if you think of the odds of a probability of 0.5, odds is 0.5 divided by 1 minus 0.5, so it gives you a value of 1. The log of 1 equals 0. So that's where that comes from. So it's a sort of a daisy chain of things you have to get to think about it. But the bigger picture is depending on your field, depending on where you publish, depending on which software you use, you may get A's and B's, you may get slopes and intercepts. The forms are different, but again, the theory is still the same. The convenient thing, actually, let's go with preference here. Even though for the rest of the week we're going to be using slopes and intercepts, mainly because when we start to get to multi-level measurement models, we start to have a random intercept, not a random difficulty. So
Not a random threshold.
that's right. So because of that, we're phrasing this as slope-intercept form this week. You often see slope-intercept form also in multidimensional IRT models as well too. So that seems to be more common with the exception of unidimensional IRT. And this is where I actually kind of like the discrimination difficulty better because the B parameter tells you where, particularly for a two parameter IRT model, so an A and a B, it tells you where a person has a 50-50 chance of answering an item correct. So sometimes we think about where it's like, we are sort of undecided. So if we order items by their item difficulty of 50-50, we can get a nice reading in the B parameter. Then we just have to order by B to figure out where that is. The intercept does not have that property at all. And so that's one of the nice things about the discrimination difficulty parameterization is that it's a little bit easier to interpret your results when you see them.
Yeah, B tells you who the item is designed for. That's the way I think of it.
Yeah. And now we're not going into this in this class, but if you're building a scale and you're trying to figure out how to optimally measure somebody, B is also for the 2-parameter model, the location where the item is most informative, meaning have the biggest amount of information about the trait itself. So, okay. So there's the slide with the IRT model. I don't think I have to go through that. Would you like to see this in R real quick? Just throw some examples, throw some numbers down on our data. This will help provide a distinction. This is the funny thing for me. My typing for the last 7 weeks has been like this. So you're going to see me looking all awkward here, which matches the way I sound. So, but let me grab that real quick. Let's see. The file I'm going to is the 01 unidimensional IRT.R file. And I have been using VS Code for my R lately. I used to use RStudio, but I found VS Code to be almost, actually there's this, I don't know if you have it here, the GitHub Copilot. Have you tried GitHub Copilot out? It's pretty spectacular. So you use VS Code with GitHub Copilot and it starts helping you with your code a little bit, which is really helpful if you don't have a left thumb.
Just as a reminder, all of the output is saved and in your download folders. You don't need to run anything.
Actually, this model is not.
It's not?
The Bayesian output is saved. Yes.
Well, my output is saved.
Okay. So here we're going to be using the MERT package to do IRT. MERT by Phil Chalmers is a great package. Has a lot of different IRT models. Many of you used MERT before? Yeah, so I don't need to go too much into it. Here's our data. Oh, nope, that's not our data. That's why.
Real life troubleshooting. Another important part of doing this stuff is fighting with R.
R and I never fight. We just have disagreements.
R and I are not usually on speaking terms.
There we go. So now we have our modeling data here. This is the data frame I was telling you about. So again, we have each student. We have their free and reduced lunch. We have their sum score. And then we have 10 items, score 1 through score 10. And here, oops, what we're going to do is take the score 1 through score 10 and just throw it in, try a 1-parameter model, try a 2-parameter model, and do a model comparison real quick. But it seems like you're familiar with this. Many of you are, so I'm just going to not do too much with it. Here, the MERT function I'm going to use is just MERT. Model is 1 for 1 dimension. The item type is Roche. And it runs very quickly, unlike the Bayes version. Here are our coefficients. You can see here.
You have to talk louder.
I'm sorry. Louder? Do we need louder? You've been telling me that all week. Evidently I have never been accused of talking too quietly in my life. That's the problem. So
You gotta beat this.
I gotta beat this. You got it. Okay, so what happens is when you ask for the model coefficients in MERT, you get an A and a D. What is A and what is D? The first question I have. Well, A, that's a clue. I'm guessing A is a slope or a discrimination. And D, then, is it a mean or is it a threshold? Good question. So, intercept, excuse me. So we could actually pull up the MERT help if we wanted to, which usually is not helpful. Oh, that's not what I wanted. Yeah, I mean, come on, like the R help, is the R help really helpful?
It is not.
But once you get down, sorry, this is very small. Eventually you'll find the model form. Where did it go?
Words.
This is not what I should have been doing. I shouldn't do this on the fly. There it is. All right. So here, what you end up seeing is, well, let's see here, 2 to 4 PL. We have a negative A plus all this other stuff. And because D right here is, there's a plus sign to it, that indicates it's an intercept.
There you go.
So D is an intercept. There, I just demonstrated the process of figuring out your computer. What is it giving you? Turns out there is an option that if you turn IRT pars onto true, you get the discrimination difficulty form. So here we have our A parameters and our B parameters, which are a little bit more familiar. You have all the A's set to 1, and we estimate the variance of theta, because we're able to do that if A is set. So we go thinking about the scale identification. This group pars area tells us the mean is set to 0, the variance is estimated, and it's estimated to be 2.595. And then we have each of the items A's and B's so far. We could also plot the parameters. Nope, that's not what I want to get out of here. That's too small. So here we have the what we call the item characteristic curve. If we had observed theta, this would be our logistic regression function. And you'll note the shape, the steepness of the curve is equal across each of the images. That is because the discrimination or slope parameter is all 1, all the same. All right? Okay. And we don't talk a whole lot about information in this class, but we could do that. This is our information. This is tells us the blue curve here, although it's hard to read, tells us where our information is most informative. The red curve is our standard error, conditional standard error of measurement for theta as you go along. You see the sort of inverses of each other. Here it tells us what our scale, our items measure roughly, the best roughly around the mean of the latent variable itself. That's what it's telling us. So we have our 10 items, have the best measurement somewhere in the middle. Anything else you want to add to that? Finally, again, we're not covering it in this class, but we will mention model fit. That's the first validity argument. There's a series of, I prefer the limited information model fit statistics, something called M2, which was a statistic developed 15, 16 years ago. Alberto Maideu Oliveira's, at least I was involved in a version of it as well. This gives you model fit statistics that you may be familiar with from confirmatory factor analysis, so something like called RMSEA, root mean squared error of approximation, Tucker-Lewis index, the the close fit index, and the standardized root mean squared residual, comparative fit index, excuse me. The thing I want to note on this is model fit to the two-way table. So this is model fit to the covariance or correlation matrix, tetracorrelation matrix of your data. So it's not, if your model fits this, it's not guaranteed it fits all of it, but it's almost impossible to determine what that means. So what I mean by all of it. Do I want to go down this rabbit hole? Okay, I'll leave it. See other places. Thanks. All right, that's 1PL. Let's go to 2PL. We just changed the item type to 2PL. Now in our output we see we have a different A parameter for each. We also see that it fixes the covariance to 1. That is because to estimate each of the slopes, we have to then set a standardized factor. That is one of the key distinctions here. We can either fix one of the slopes to a value and then estimate the variance, or we can estimate each of the slopes or discriminations and then have to standardize the factor. So our scale is identified between 0 and 1 now. Mean of 0, variance of 1. We have all of our A parameters. And then we have our item intercept parameters here. And if you wanted to look at the IRT parameters here, the main thing here is the A's are the same. The B parameters are different. This tells you where the items are most informative, right? So we have low difficulty or easy items here. Like the easiest item is number 6. And then the highest difficulty item looks like it might be, what's that? The very first one here, 0.986. So, again, we could plot here. I'll plot the trace lines here, the item characteristic curves. You'll see they're not parallel, but some of these look really nice. I mean, what we talk about in terms of this right here is why we call it the discrimination parameter. Between small ranges of theta, we go from 0 probability of answering it correctly to 1 probability. Did I see a question or just?
Sorry.
No, it's okay. It's okay. I'm like, please ask a question. Please. No, I'm just kidding. That's good. Okay. But yeah, about the same. It sounds like most of you are very familiar with this. If you're not and you need more description, just let me know after class. I'm happy to talk with you individually as well. We can see if this model fits. I would say this model is, well, normally we see an RMSEA like that. We kind of like it, but marginal. Ironically, for these data, which the rectangular state that I worked in paid millions of dollars to get, did they do model fit? No. But they report all the scores to all the students, and their parents look at all their scores and so forth just the same. Finally, the one parameter model and the two parameter model are nested. One parameter is nested within two, so we could do a likelihood ratio test since we're in a maximum likelihood framework. We can see which model fits best, and oftentimes this result happens. We have 9 degrees of freedom as a difference in terms of parameters, and this tells us that in this case the null model is the 1PL, the 2PL is the alternative. With the p-value of 0, we reject the null model, and we think the 2PL fits better, and that is common in the data I work with, at least, quite frankly. I don't know. Have you ever compared Roche and 1 and 2PL? Yeah. Okay. Yes, this is a question.
This is a question.
Gotcha.
You said that for identifying the model, you have to use a standard normal for the theta or fix one slope.
Correct.
H1.
Yes.
Do we really have to use a standard normal, or can we just fix it to any, fix them to any value and then the interpretation?
Technically, you can fix it to any value. Practically, depends on how they coded it. So what I mean that is, if you wanted to have a mean of, let's take a scale like, what's the mean of the GRE these days, 150? So put a mean of 150 in here and a variance of 5 or whatever the variance is. There should not be mathematically nothing wrong with it, but if the starting values of the program are such that if you don't supply them and they pick them randomly, they may pick them so far that when they take the exponent, it exceeds the numerical precision and becomes not a number. So theoretically, yes. Practically, you may have to also supply some starting values to make that work. Good question. Other questions? Yes?
I'll take it personal. I just feel like I'm missing a little bit the bigger picture here, but I'm never doing IoT or anything. So could you briefly explain again why for multi-level modeling we're now speaking about probits, about select making it right or wrong? I think I missed some.
That's a great question.
Measurement model and this.
No, this is perfect. No, please don't. I'm glad you asked that. And actually, I encourage any questions like this because it's very important. The big picture is this. Tomorrow or when Lisa talks, we're going to take the sum score and do multi-level modeling with it. But that sum score has a problem. It's not perfectly reliable. So to build a multi-level model appropriately, where we are predicting the latent variable, we need a simultaneous model, where we take a multi-level model and put it on top of the item response model itself, so we don't have to output the sum or the theta estimate. So that is a great question. I apologize for not making that clear in the beginning, but that is a fantastic question, because when we do the model analysis simultaneously, that missing reliability part where theta just has error now is incorporated into the model itself. And so what we will end up having in the full multi-level model is this measurement model to begin with, and then now theta will be nested within school. So we'll have a school theta and a person theta as well. I hope that helped answer the question a little bit. Okay, great.
Yeah, so today is wrong because we're pretending the students are independent. Tomorrow is wrong because we're adding shit up and calling that an outcome without a measurement model confirming that that's okay. And the fact that we just found that the 2PL fits better means that that theta is not the same thing as just adding shit up. That's the 1PL model. And then by the end of the week, we'll try to stop being wrong and put it all back together again at the same time. But we didn't want to start there.
Yeah. And if I could be clear, by the end of the week, we'll be wrong in a different way. That's the headline for the last model of the class. It's the CFA police. Or is that an ambulance?
They heard you were ignoring clustering.
Okay. Other questions on any of this? Okay. I should also mention, I didn't put it in here, but if we could output theta from this analysis. We can get a point estimate of every person's latent variable as well. That's typically what when you take a large-scale assessment like the GRE. That's what happens. That's where your score comes from. Ironically, another side note to this: when I worked in a psych department, the dogma is we never use factor scores; those are bad. But then we turn around and we use GRE scores, which are factor scores, which is sort of the outputted theta, the latent variable itself, is a factor score, but it comes from IRT. I don't know if you've ever had that before. Have you ever heard, don't use factor scores are bad, there's indeterminacy and all this other stuff? But then you take a test, and guess what they do? They sell you your score is a factor score. You're buying it, right? So I make this joke in my class last year. In my program, a lot of the students end up going into the testing industry. It's like, what do? We're selling thetas. We're in the business of selling thetas, right? So
Just without the standard error that goes with them. Don't ask too many questions about where the data came from.
yeah, that's terrible. All right. Anything else? Any other questions? Okay. Now, so summarize. Latent variable models are all over the place. You said which measurement model to choose from. Do I pick IRT? Do I pick graded response? I didn't. I only showed CFA and and basically the 2-parameter binary IRT model for binary data. But the labels of all the models tend to imply a different distribution for each. So if you have Likert data and you want to treat it as categorical, the labels we use are often something called graded response model, which falls under IRT, but it does the same type of work. There's other models for other types of data as well, too. The key in this is the theory. The latent variable shows up on the right-hand side. That's the same regardless of the type of the data you have. You may see different parameterizations, like the slope-intercept versus discrimination difficulty. And then for like graded response models, you may see more, Lisa, you call them submodels. You may see more like model equations, but that's because there's more parts to the analysis as well, too. So the long story short of this section was we wanted to provide a common framework to talk about measurement models, because to do the multi-level measurement correctly, we have to have the measurement model in place to begin with.
I'll add 2 more things. So if you have a distribution for it, it can be a measurement model. So if you have a count variable, number of alcoholic drinks you have in each, number of cigarettes you smoke, like things like that, you can put that into a measurement model. And not all the items have to be of the same kind. You can mix and match. You can have some binary items, some continuous items. You can have ordinal items. You can have a latent variable that predicts all different items types at the same time. It doesn't have to be one size fits all.
Yeah, we tend to teach IRT. Well, in our program, we teach IRT as a separate course, and then your version of factor analysis combines it all, which is nice. But often you see factor analysis by itself. You'll see item response theory by itself. You'll see, I don't know, whatever else shows up there. What we're trying to do is both at the same time, to try to understand the nuance of both. So, okay, how are you with Bayesian statistics? So, all right, okay, no, okay. Well, this set of slides is just what Bayes is. All right, so we got measurement models. Now we're going to do Bayes. And then guess what we're going to do? We're going to put those together. Measurement models with Bayes, all right? Sorry.
I was going to say, so the Bayes is required to estimate the measurement models.
That's right.
That's the connection.
So the multi-level measurement models are horrible to estimate. What does M plus do often for you? Does it blow up? You said that's your technical term for it is it blows up?
Yeah. It goes sideways, blows up.
It doesn't end up estimating very easily in maximum likelihood. There are occasionally, I think you described to me, like the cases where you've seen it work successfully, usually are simulated data examples. But when you get real data, things go bad fast. What do I mean by that? It will not estimate at all, right? And so If you use M+, I don't. I don't like the black box of M+, so I try to do anything I can to like not use M+, but if you use M+, I'm sorry, I'm not judging. Levon too.
It's the same problems.
M+ will flip over to Bayes. You have the estimator equals Bayes option,
Yeah.
so you end up having to do Bayesian statistics for it as well. So what I'm hoping here is, let's talk a little bit about what Bayes is doing, and then we'll put it in the context of the measurement model next, and so we'll try to build forward from it. Tomorrow, whenever we get to the next section, Lisa will introduce multi-level models, and then I will show you what the Bayes form of those look like as well too. So we're sort of trying to parallel build toward this final destination of multi-level measurement models. Okay. Think about a question. Just one moment here. There we go. Okay.
They heard you.
The Bayes police are here now. Okay. Thank you. Anyway, yes. So just from a basic point of view, Bayesian statistical analysis refers to the use of models where some or all of the parameters are treated as random components. That means that each parameter has a distribution attached to it. Right? So think from that last set of slides, it's like saying I'm going to put a distribution on the item intercept, or I'm going to put a distribution on theta, or factor loading. So we form a likelihood function, which is what we form in every model when we estimate it with maximum likelihood. And that likelihood function, the data itself, gets augmented with that additional term or terms that represent that distribution for the parameters. That distribution for the parameters we call the prior distribution. So the prior distribution shows up on each of the parameters. We have our model distribution, data likelihood, as well. And we combine the two to provide our analysis. Think of this as saying each parameter has a certain likelihood. You have a belief as to what that parameter might be, right? So if I have this measurement model that I just estimated, and I believed each of the item discriminations to be bigger than 1, I might pick a prior distribution to sort of to put that belief into place. Final estimates then, when we complete our Bayesian analysis, are summaries of a posterior distribution. Right? A posterior distribution is a distribution that combines the distribution of the data itself, the likelihood of the data, model data likelihood I call it, and the prior distribution. We say it's proportional to. Right? So we end up getting, there's many different ways of estimating a Bayesian analysis. Most commonly is Markov chain Monte Carlo, but that's not the only way, right? There's ways of doing, looks like maximum likelihood, optimization-based versions of it. But if we use Markov chain Monte Carlo, we actually get a sketch of the posterior distribution itself as our output. Like it's just this like histogram, if you will, or a smooth density. So we have to summarize it somehow. So we take a summary, like a mean, and we say this is our parameter estimate. And we may want to put some error bars around it, so we figure out what those error limits of the distribution might be, and we call it, this is the range we believe the parameter to be in. So in the Bayesian sense, what we end up doing is our whole goal is to estimate the posterior distribution for each of our parameters, and then use that to make inferences. Well, let me keep going here. Why are we using Bayes? Right? Because let's be real. Bayesian analyses are way harder for the simple models than what we just did to quickly run an IRT model. I just ran an IRT model, it ran in less than a second, we have our output, we have inferences, it's no big deal. I think there are 4 main reasons why people use Markov chain maximum likelihood. So remember, Bayes is not MC, but we will be using MC as our Bayes for this class. One is missing data. You can easily incorporate missing data into an analysis, basically thinking the missing data is a parameter itself. And so now in the Markov chain, you are sampling values of that missing data. 2, this one, in this day and age, 2023, lack of software is less of a problem, but it's still there. That's actually why I got into Bayesian statistics in the first place. I was handed an algorithm and a model and said, doesn't work, fix it. It's like, I don't know about Bayes. It was in Fortran. I don't know about Fortran. I didn't know about Bayes, but that was my research assistantship in grad school. So that's what I got into. So this is still true, though, in several classes of models. In particular, multidimensional item response theory is very difficult from a pure maximum likelihood point of view. We use something called marginal maximum likelihood. We have to integrate across the latent variables. When you have one latent variable, like what we just did with MERT, it takes, I believe, 61 quadrature points. So it breaks up, it puts a distribution on theta, and it sort of breaks that continuous distribution into a series of quasi-continuous
Rectangles.
rectangle-like shapes to try to. Yeah, thanks, Siri. But when you have two latent variables, now instead of having just one dimension to integrate over, now you have two. So you have 61 points on one side, you may have 61 points on the other. So now instead of summing 61 points for each person at each step of the algorithm, you have to do 61 times 61 points. Now, MERT's default does not 61. It actually lowers the number of quadrature points as you move up by dimension. I don't remember what it is for 2. But the point of the matter is, whatever it is, it's quite hard, and it takes a very long time. In a Bayesian analysis for the same method, it would not increase in computational, it would take a few more calculations, but it's not that exponential increase in calculations. Another reason why you might use Bayes, or MCMC, is that you can create your own model itself, right? So if you come up with a brand new model, you come up with models that are not readily available to you, okay. Bayesian statistics has a sort of a general likelihood sense built into most of the packages people use. You can come up and estimate those models very easily. Finally, people use Bayes for philosophical reasons. I kind of refer to them lovingly as the cult of Bayes. Is anybody a proud member? I'm not, but there are some people who are like, no, the posterior distribution, it is something different about it. It's sacred, right? It's this brand new thing I need to have because of the way we treat data and because of the philosophical point of the likelihood, and it's not at all, I don't know. So we're doing Bayes in this class because of really number 2. There is software capable of handling it. The speed of the software is questionable, and the ability to add prior distributions to sort of put more weight on different parts of a likelihood function makes it so it's more likely to converge and produce results that we need rather than otherwise. So, any questions on Bayes so far? All right. So Bayesian statistics is super controversial, or it has been. I think it's much less so now, but it can be, because if you think about it, the prior distribution may influence your results, and you get to pick the prior. So what's to stop you from saying, I'm going to pick a prior that ends up being the posterior distribution? I think my data look like this, so therefore I'm going to make my results look like this. Right? Nothing stops you from it. So yes, the use of certain prior distributions that can produce results that are biased or really are subjective judgment rather than objective science. That's one of the biggest complaints about Bayesian. We sort of get around that because if you publish a Bayesian analysis, typically it's good practice to report what your prior distributions were and why you picked those, right? So people can evaluate those. And you can imagine, was it reviewer 2 that's the problem? Reviewer 2 will never like your prior distributions regardless, right? That's always the fight. So Bayesian is annoying. In addition to taking a long time, it's also annoying, but it works. The other issue with Bayes is that most estimation methods are really computationally intensive. So for every parameter in our model, we are literally at every iteration of the algorithm sampling a new value. We are sketching in its posterior distribution. So think of that. In an item response model that we just ran, we have 10 items. So that means we had, let's take the 2-parameter model. We had 10 A parameters, 10 B parameters, 10, item intercepts, 10 item discriminations. But we also had 3,100 thetas. So every iteration we are sampling 3,120 parameters, right? That's very computationally intense. And not only that, many of the easy Bayesian programs. So if you're not rolling your own Bayesian, like if you're not building your own from scratch, like you use Stan, right? Stan takes a lot of syntax, right? You have to phrase a model, you have to phrase the parameters, you have to phrase the priors, you have to phrase the data. So it takes a long time to build the syntax as well too, and that's the easy Bayesian. So I'm really selling you on Bayes here, aren't I? You should really use Bayes.
Well, estimator equals Bayes is the easy Bayesian.
True, but then what is it doing after that? Fair. So a lot of, in particular in psychology, I think we've come very far in the last 20 years. But there's still sort of this battles about whether we should even use Bayes, or if you use Bayes, where you're using it the right way. I mean, there's all sorts of, I would call it nuanced arguments about which priors you should use for variance or whatever else. But anyway. But thankfully, Bayesian methods have become much more widespread in the last 20 years. They're getting better and better. We use them in quite a few different places. So let's talk a little bit about how Bayesian statistics work. You've probably seen this. This is the equation you probably saw in introductory statistics. It still applies. We are using Bayes' theorem. Bayes' theorem would say, let's take two discrete outcome events A and B. The probability of A conditional on B is equal to the probability of B conditional on A times the probability of A divided by the probability of B. Sometimes we take the denominator out and put this weird proportional symbol in and just take the numerator to it. But each of these terms has a definition, and they all apply in what we do as well. Here, A, our probability of A, right here, this guy, right there, that is the prior distribution of A occurring. Right? That's something that, when you begin with, you specify, basically. What's the prior distribution that A happens? B is the marginal distribution of B. What's the probability you just observe B, not conditional on A itself? The probability of B given A is sometimes called our model data likelihood. That's what I use the word for. I don't think a lot of people use that terminology. I like to use it because it ties it to what we do in maximum likelihood. It's the conditional distribution of B given A. And finally, the thing that we all are working toward is the posterior distribution of A given B, right? So here, the posterior distribution of A given B comes from a sequence of parameters. So what does that mean for us in psychometric land, right? When we get to psychometric models, what we're after is the posterior distribution. Let's say we're looking for a person's score, theta. We're looking for the posterior distribution of theta conditional on the item responses they gave us. So if we go put this into the this framework, which I'll do a little bit later, the likelihood itself is the likelihood of the data given theta, right? And if you remember from the last set of slides with the probability y equals 1 given theta, that's it. Data, y, theta, a, right here. Right? So that's where that shows up. The prior distribution of theta, turns out, I think behind the scenes in MERT, we assumed a univariate normal distribution. So we already had that in our analysis before. We say that theta follows some normal distribution. In the two-parameter case, the mean was 0, the variance was 1. This term at the bottom is somewhat difficult to arrive at. You sort of have to integrate over this space, but that's actually why Markov chain Monte Carlo exists. We can come up with ways to shortcut that integral to not have to do the integration as well. So that is the thought of what Bayes does. So we are literally, our version of A is going to be our model parameters. Our version of B is going to be our data we observed. Right? So posterior distribution of the parameters given the data. Now, if you're into like likelihood functions, the weirdness in all of this is this term right here is the same likelihood we use in maximum likelihood when we use maximum likelihood estimation. So there's a core of Bayes that's the same that we've had from before. And actually, it's actually notated differently in maximum likelihood. Sometimes we call this the Bayesian flip. If you read a maximum likelihood book, this is usually A given B, but that's our data likelihood. Where we call it in Bayes, oh, that's our distribution of the data given A. So it's this weird notational difference, but from a computational point of view and from a mathematical point of view, they're the same likelihood functions themselves. The core of Bayes is the core of maximum likelihood. And so what that ends up doing is, if you start thinking about Bayes as fringe, like weird, right, out there, you're using the same likelihood, which means, turns out, all the cool things why you'd want to use maximum likelihood. Like, why do we use maximum likelihood? Apart from like all the packages use it. There's some nice mathematical properties from maximum likelihood, right? As the number of observations goes to infinity, you have some very long-running classical statistical theorems that talk about what your parameter distributions converge to a normal distribution. They become unbiased. We can set what the variance is under certain conditions, the regularity conditions, and so forth. Because that likelihood shows up in Bayes' theorem, all of those apply in Bayesian statistics as well too. So it's less fringe and weird. It's almost like the cousin of maximum likelihood with a bit of a different term right here called the prior. Okay? All right. So you can tell I'm not one of the philosophical Bayesians. I like to think of I do the practical Bayes, right? I have Bayes because I have been working with models that nobody had software for at first, and then second, take forever if I use maximum likelihood. So let's try a little example here. Let's imagine we wanted to assess the probability of rolling a 1 on a 6-sided die. Now we know in the long run, if the die is not, if the die is not weighted in some way, the probability should be 1/6, right? We can collect a sample of data, 0, 1. So here, a 1 occurs if we see a 1, and a 0 occurs if we got another number from 1. These are we call these independent tosses of the die itself, right? So now what we're looking for, what we want to assess is the posterior probability of a 1 conditional on the data. So that's the probability of this parameter conditional on our data. And we can put that into Bayes' theorem, the probability of our parameter, the probability of 1, given x, our data. We'd have to specify a prior distribution for that. And we can calculate this with numbers. So the first thing we have to do is define the likelihood function itself of the data. This likelihood function, believe it or not, is very similar to what we just saw in IRT. In particular, that part. Right? If we define a success as seeing a 1 and a failure, or a 0, as seeing something that's not a 1, we have a Bernoulli distributed variable. Right? So for any one roll of the die, we have a Bernoulli distribution describing the likelihood that that event occurs. Right? And the distribution itself, the mean of that distribution, is the probability of seeing a 1. So the trick in all this is now if we have 5 pieces of data, how do we build that joint likelihood of all the data? Here, because we can assume each roll is independent of each other, we take the product across all of the 5 rolls. So this would be the product from I equals 1 to 5. And that builds the big component, the core component of the likelihood itself, which is this numerator part in Bayes' theorem right here. So for item response theory, the only difference will be this thing is not P. Now we substitute P1 there for our probability given by the item response model for an item. Right? So the trick in converting like this simple Bayes example to something more complicated is the likelihood function represents your model. That's where your model goes. Right? And your model, as we talked about before, previous to this, when we look at a psychometric model, our model is for the observed data. Every observed variable has a distribution. Turns out every distribution has a distribution function, and that's what shows up here. So linking this to our prior slides, previous slides. This is trying to tie Bayes to psychometrics in a way that says when you make that distribution assumption, when you have a measurement model, the measurement model name usually implies the distribution of your data. That in turn helps us build the likelihood that we use in Bayesian or in other estimation as well. So we can actually visualize this likelihood function. This is the log conditional. So this value on the x-axis here is a value of p, like some just value. So it can range between 0 and 1. We know the right answer is somewhere down here, 1/6. Right? But this is the likelihood function for one roll of the die for p. And this is the log of that probability given by this Bernoulli distribution right there. Now, here's the trick. What's our prior distribution for our parameter of entrance P1, right? The probability of seeing a 1. This is the problem with Bayes. Lisa, which prior would you pick?
I don't know, dude.
So we need a distribution that has a range or a sample space that matches the sample space's parameter. What P1 is a probability, so it ranges between 0 and 1. So you can't say normal, because normal doesn't range between 0 and 1, or you can't say normal very easily unless you truncate it. But it turns out there is a distribution that does range between 0 and 1, that's beta distribution. I have a kind of a love-hate relationship with beta. I don't know about you. Anybody used the beta distribution in modeling before? Yeah. Is it finicky? It's hard to use sometimes, I feel like, yeah.
I will pay you $1,000 if you can tell me what alpha and beta mean.
This is the shape, and this is the scale.
Oh, those are words. Tell me what they mean.
Well, anybody want to accept the challenge? Now, the conversion from dollars to euros isn't quite
Dollars are like 10% higher, right?
lower.
Lower? The other way?
Yeah,
Okay.
it's like 90 cents of a euro for $1. So
That's where I get stuck. I have no idea what that means beyond shape and scale. No idea.
So yeah, so we get into the voodoo side of Bayes now. You pick a prior, you may not know the distribution. It gets even better, right? I mean, we could pick, anyway. Turns out, this is beta. This is the distribution function. And just again, I'm putting the distribution functions there because they're mathematical functions, right? If you plug in P1 and you set a alpha and beta here, it will return to you a height. That's all it is. The likelihood that you see P1 given a alpha and beta that you picked. And all this is, yeah, anyway, the beta distribution is funky. Hey, by the way, the mean of the beta distribution is alpha over alpha plus beta.
Well, that clears it up.
And here comes some more notation. Because we talk about the parameters of the prior distribution, these parameters are called hyperparameters. Yeah. Right. But we fixed these. Turns out in some, tomorrow, when we talk about multi-level, the hyperparameters might get estimated. That's called empirical Bayes. But in here, we're fixing the hyperparameters to values. So we can pick values. It turns out we could pick values of alpha and beta that correspond to our prior belief. What's the likelihood of rolling a 1? 1/6. So if we pick an alpha of 1 and a beta of 5, you'll note that the mean then turns out to be 1/6. Right? Similarly, if we pick an alpha of 100 and a beta of 500, that also gives us a mean of 1/6. What's the difference? The difference is how strongly we feel that 1/6 is an appropriate prior, right? Turns out the beta distribution also has a variance. It's this ugly formula up here. And look, there's a typo. There's an extra parenthesis at the end.
That doesn't count.
I know. No, that counts. It doesn't change the meaning of it. It just looks weird. Here, choosing alpha 1 and beta 5 gives us a prior with a mean of 1/6 and a variance of 0.02. The variance, 0.02. That doesn't mean a whole lot by itself, but look at what happens if we did 100 and 500. The variance is 0.0002, right? It's quite a bit smaller. So think about that. When we are very certain of things, we want a variance that's very small. That's called That is called an informative prior. I have to choose my words slowly there so I don't run them together. Informative prior, small variance. Right? On the alternative to it, uninformative priors have large variances. Right? Yeah, the mean may be 1/6, but this variance is quite a bit larger than that variance. Right?
It's still not very large.
No, but we're talking about small numbers anyway. So here's the difference between the two. We can visualize them, right? This is the result of the beta distribution. So again, P is a hypothetical value of the probability of rolling a 1. And the height over here is the result of this beta distribution function right here. Right? So you plug in a P, you get a height. The higher the value on Y, the more weight that places on where the posterior distribution will be. Right? So if you say, I'm really certain that the probability is somewhere around 1/6, this dashed red line is your distribution. Right? It has that peak, really, really high likelihood right there. That literally is multiplying the numerator in Bayes' theorem. Right? You get your component that comes from the data, and you get your component that comes from the prior. And if that prior distribution has a really strong weight, it contributes most of the mass of that posterior distribution, and that centers where your result will be. Alternatively, this black line is your uninformative prior, and it looks relatively pathetic, but the mean of it still is the same mean. The means are the same, the shapes are very different. That's beta for you. Any questions? So let's tie this to statistics, right? What's our prior for a factor loading? I don't know. How would we pick that?
Depends on if you want to cheat.
Yes. I think a factor loading should be normally distributed with a variance of 0.0001. You're going to get a result where the mean of the posterior distribution is the same, right? Where your mean of the prior is. If I do the opposite, I want a prior distribution where say I think it's normal and the mean is 10,000, I probably won't have much influence from the prior itself. So, in my use of Bayes, my Bayes practice is kind of like yoga, right? It's like practicing Bayes, you practice yoga. Anyway, never mind. Sorry, tenuous. But I try to do as many uninformative priors as possible. I don't particularly care for priors. The only times I start to make things more and more informative is if I don't get convergence in my estimation. So that's my own way of working in Bayes. Any questions so far? Okay. So it turns out this posterior distribution is very convenient because when you take Bernoulli data, or a binomial, and you put a prior on the mean that's a beta prior, the posterior distribution you can show with mathematics is also a beta distribution. Like you can derive it, you can prove this, right? Why that's convenient, or this choice of prior actually goes by a name. We call it a conjugate prior. A prior distribution that's the same family as the posterior distribution is a conjugate prior. Whether or not you choose a conjugate prior these days doesn't matter. Back in the old days, the conjugate priors were important because we didn't discover some of the Markov chain algorithms. I shouldn't say that. They've been around for a long time. We didn't know about them in the social sciences until 20, 30 years ago, right? So without that, conjugate priors were your only way of really doing Bayesian statistics. These days, you can pick any prior. It doesn't have to be conjugate. There's nothing magical about conjugate effect, apart from it may estimate things a little bit more quickly. But what do I mean by that? You can show that the distribution of the posterior distribution, the posterior beta distribution, right? Remember, beta has an alpha and a beta, right? The alpha from the posterior is your prior alpha, or A in this case is what I'm calling it, plus the sum of successes that you found. And your posterior beta is your prior B plus the number of failures you have, right? The number of times I've rolled the die minus the number of times I saw a 1. Right? So what this ends up doing is it shows us the connection between prior and posterior. If I had chosen a 1 for my prior alpha and a 5 here, you'd see the impact of the data would be much larger, right? If I had chosen a 100 for alpha and a 500 for beta, the impact of 5 observations would be much smaller, right? So the conjugate prior in this case helps us see how the impact of prior is mitigated by the size of data that you have. A little bit. How's this going? So far, so good? All right. So here's a posterior distribution for those 5 observations, right? Actually, I think this is 1 observation, excuse me. If I roll 1 observation with that conjugate prior of A of 100 and B of 500, that's my posterior distribution. It sure looks like the value. So, and then if I have a 1 and a 5, you'll see that this is my posterior distribution. This is the output of Bayes, posterior distributions. Not parameter estimates, posterior distributions. That's weird, right? Yeah, I get that. I appreciate that. And Siri wants to talk again. Anyway, Siri just really wants to teach statistics, which sounds like a nightmare. Or maybe better, I don't know. The posterior distribution is just the whole distribution. So how do you summarize it, right? So let's get to think about that here a little bit. Again, think of where the mean of this distribution, because this distribution is symmetric, mostly symmetric, we can put the mean somewhere right about the central part, which is right about 1/6, right? Right here. And so if we compare the mean of the black line to the mean of the dashed red line, you'll see the mean, the black line is right here, 0.35-ish or so. Right? So if our point estimate that we're trying to talk about, the average, the central tendency of the posterior distribution is close to what we expect it to be versus not, pardon me, what I'm trying to say is that we tend to pick measures of central tendency and variation, the basic measures that you learned in basic statistics, to describe our posterior distributions. We talk about its mean, sometimes we talk about a median. Don't often talk about mode because they're very hard to calculate numerically. There's 18,000 methods of calculating a numerical mode.
That's maximum likelihood.
Yes, it is. And sometimes we talk about some type of interval around it. So like a confidence, and we call it a credible interval, right? What's the range the parameter should fall between? So here, if we were to describe how much uncertainty we had in that estimate, we'd say, oh yeah, the mean estimate for the dashed red line is about 1/6, but it may vary between, 0.15 and 0.21, right? Where the sort of confidence limits are, percentiles, quantiles of the distribution itself. Whereas this black line, we'd say, oh, the mean's about 0.35, but we're really uncertain. It could be as low as 0.1, could be as high as 0.6. So what I'm building for you here, I'm trying to build for you here in your mind, is when you're using Bayes, you get a posterior distribution. How do you describe it? Well, let's think about it. We can talk about its mean. We could even calculate its standard deviation, right? So mean is usually the equivalent of what we talk about with maximum likelihood point estimates. It's not exactly, but that's the number that we report. The standard error that we would typically talk about is like a standard deviation. A confidence interval would also be calculable, although we call that a credible interval as well too. And there's several forms of that. So all the statistics that you would see in maximum likelihood, like we just saw when we ran MERT with a number, that number more often than not that comes back from Bayes, it's its mean of the posterior distribution to describe it. Any questions? All right, here we go. Yep, so sorry.
Now we had a dice and we assumed, because we know there's 6 options and it's 1/6, what do we do if we don't know about it?
Great question.
A and B?
Yeah, that's exactly right. My preference is to start with, I assume very little. In fact, if I had picked A of 1 and B of 1, that's a uniform distribution. Beta is flat throughout. I find that to be the most uninformative prior there could be, because it's literally putting no weight on any value of the parameter itself. So in my use of Bayes, my belief is do the least amount of harm. Put the least amount of subjectivity into the analysis. Believe it or not, that is controversial to the Bayes folks, because they believe that Bayes you should express your belief. But if you don't have belief, if you have no certainty at all, shouldn't the prior represent your uncertainty? You study judgment decision making. This is like a belief. This is very much judgment decision making task. Like, where do you put your belief that something is about to occur, right? Exactly. I used to, one of the experiments I did for my master's thesis was about asking people the amount of calories or kilocalories in food. And I would basically say, what's the subjective probability you have that the pear has more calories than the banana, right? It's like, what's your probability? And so you would assess that. That same process is what we're saying here. What's your subjective probability of thinking that a 1 will occur on a die roll of 6? Or putting it back into our class context, what's your subjective belief that a factor loading will fall somewhere between 1 and 3 or something along those lines? I hope that helps a little bit. Lisa, do you have anything to add?
And also keeping in mind what is logically possible for the parameter to be. So I mentioned cheating earlier sort of as an example. This is one of your homework questions for 10 years ago or something. If you think that all of your items are going to have positive loadings, right? When, more theta means more likely to get it right or more likely to endorse this item, then one way to make sure that happens is to pick a prior that doesn't have any negative numbers, right? Then it's it can't be negatively related. There's no more bad items. Fix that problem.
It actually comes up quite a bit when we get to the Bayes measurement models. The factor loadings themselves, you'll often see priors that do just that. They use a log normal distribution, which does not go below 0.
That's cheating.
I think so. I think how many of you have estimated a measurement model and had a negative factor loading? Usually you see them in more complicated models like multidimensional or like a bifactor model, that type of work, but it's possible.
No, I've seen that happen where you have a negative loading, meaning the item works backwards. More theta means you're less likely to get it right or less likely to endorse it. It can happen. I've seen it in international research for translations that went awry. So they did not translate the item accurately and they did not capture whatever the item was supposed to measure, and it actually worked backwards. So I think allowing that to be possible, it depends, the extent to which you pick your prior dictates what you can logically get back.
So it's hard to choose what that is, but that's it. So again, the summaries, this is the mean, 0.36. These are the formulae, by the way, that I used, that showed you for the mean of the beta and the standard deviation or variance of the beta, right? So the mean is for the uninformative prior, the mean was 0.36 and standard deviation was 0.13. For the informative prior, the mean was 0.17, very close to what we should expect it to be, the standard deviation of 0.01. And again, that standard deviation is analogous to the standard error in the maximum likelihood world, right, where the parameter could be located. So now we have this little example. I'll just show it real quick. What we're actually about to get into is a world of what we call Bayesian updating, right? So here, let's grab this real quick. This is in my workshop. This is actually in the slides as well too, but I wanted to set this off a little bit in a different way. Yeah, actually I don't know that I have it. Where did I put it? I had created a file yesterday evening, of course this is why, because I was tired when I did this, that had the Bayesian version of what I'm about to do here, but I don't think I have it available unless, yeah, I don't know where I saved it, but that's okay. Here. I apologize for the delay. No, that's not it.
We have lunch in 15.
I understand. We're going to get through this. Anyway, the point is, let's do this. I'll just give it theoretically. Okay, so let's imagine we do one die roll, and it's a 0. It's not a 1, right? So that likelihood itself, what we end up going from, these are our prior distributions here, right? Before we observe data, all we have is a prior distribution. It's like a posterior distribution, right? It's like we have no data to work with. Once we roll a 0, we can update our belief, and then it becomes something that looks like this. And the more we roll, the more we add data. Basically, every time that we add another observation, the prior distribution could be the result of our posterior from before. So every time we add more data, it gets more and more like what
It's
happened.
under slides.
Slides.
Or in Dropbox. Bayesian updated.
There it is. Thanks. I'll just do this quickly. All right. So prior distribution, 1 and 5. This is our uninformative prior. We roll the die. We get a 2. So our new observation is a 0. We update our posterior, and we make a plot that looks like that. That's the plot that I was just showing you on the slide, like that. Now, let's imagine we collect a new, and then what we do is update the A and B to be our posterior distribution. So now, before we collect that next observation, we could say our new prior, our new belief, is what we had just observed from our previous analysis, right? So let's imagine we do roll a 1 this next time. So we can then go and plot, and now our posterior distribution starts to take this form, right? So the informative prior is the dashed red line, the uninformative prior is the black line, and you can see that we're starting to get a sense for what that distribution should be. Then we update the values of A and B, and we do this one more time, not there. And then we say we roll a 1 again, and now we're starting to look a little bit more like what happens. So every time, one of the unique parts about Bayes that people like, particularly from statistics, is you can think of every time that you add more data, it's like you're updating your belief about what the parameters should be. Now, we don't often see that in the psychometric world. We just fit a model with our data that we have and take our output and call it good. But you could think of this as interplaying with, we talk about the model fit discussion, right? If you fit a model and you have to go and adjust your model because it doesn't quite fit well, that could be your next prior distribution for when you collect new data. Okay, this is my new data, and so now I'm going to update that prior as we go forward. Or in the case of maybe educational measurement, if we're worried about what a student's learning throughout the academic year, we may give an assessment in September or October or November, and every time we update with our belief about what the student knows, the output of 1 becomes our new belief or prior for the next set of data that we collect as we move forward. So one of the things that Bayesian presents as a methodology that is helpful is this idea of Bayesian updating. Okay. Any questions? Quick tour through Bayes. Everything's going to be quick. Probably not quick enough.
Is that what they use in compiling polling data over time?
Yeah, so I don't know if, in the United States, we have this, like nearly 20 years ago, a guy named Nate Silver started something called 538.com. So we have this guy who takes, we have this weird election system where it's like for president, we have each state has to vote separately. We have these statisticians who do Bayesian statistics who basically take like survey data, people who, you call, who you're going to vote for. And every time they grab more data, they sort of update where the Bayesian belief is as to who will win the election and so forth. And so these are most notably interesting because in the last few elections, they've been terribly bad at predicting who's going to win, because nobody wants to tell you who you're going to vote for. They're so tired of having people call you and say who you're going to vote for and all that stuff. So unless they don't know how to sample well anymore in the age of cell phones and email and text messages and so forth. But that is a huge key in this. Or anyway, there's lots of other fun things you can do, like, oh, you want to bet on sports. Okay, have a prior distribution about who's going to win a game, and then after that result, update your prior and keep moving that along as well too. So it's an odd part, but I think the updating part for us, we don't see it a lot in the psychometric world and the measurement model world, but it could be something that's useful. We just haven't gotten to that part as much yet. I think particularly when we talk about updating our belief about a latent variable, if we're in a study that's measuring people over time, we may want to update that belief if it's the same trait as we go forward. So the key in all this, just the notation, in addition to the numbers, a prior distribution is your belief, right? The parameters of that distribution are called hyperparameters. Depending on how you form them, depending on how much variance in that distribution there is, they're either uninformative or informative. And a conjugate prior is a prior that has the same distribution family as the posterior. But again, we won't mention conjugate prior very often. It just helped us in this example where we didn't have to use a different estimation method to figure out the shape. The posterior distribution itself, this one, is formed by the combination of prior distribution and the model, the data likelihood. And the data likelihood is your model, right? So when you specify your model, you're actually specifying one component of the Bayesian analysis. The second time, the last bit of components to do if you're doing a Bayesian analysis are the prior distributions. So up next is MCMC and Stan. And the look on her face is, I don't know what the right word is, but let me stop here and ask any of any questions about any of this, especially while the siren goes by.
This might be a good start.
That sounds good. Is that the Stan alarm? Is that like, someone said Stan. How many of you use Stan? Not, yeah? Right. Anybody else? Yeah? Okay, so not many? A handful? Okay, good. So I do have slides on Stan, so we're going to bring that up. But if you have Stan in use already, this probably isn't going to help you, but it'll be the foundation. Any questions on what we just discussed? There's one other thing I will add, one last thing. So this shape that you see here of this prior distribution was formed because we had that conjugate prior. We knew it was beta, so all I had to do was use the beta PDF function in R. What was it? P beta, I think it is, right? Or D beta, excuse me. D beta, that function in R, and plug in the new alpha and beta and the value of P, and it will draw it. If I didn't use a conjugate prior, I still want that posterior distribution. That's what MCMC is for. The MCMC alarm. Pause. Sneak a drink. What MCMC ends up doing is providing literally a rough sketch of that distribution. It's almost like, have you ever taken a piece of paper and etched like a monument or like a plaque where you can etch it over and you get a kind of a resolution of like a piece of pencil, a pencil and a piece of paper and sketch it? That's what we're going to do with MCMC. We're going to sample values, and at the end of the sampling of values, we're going to draw what those values, the shape of the distribution those values give us. And so because we don't have this conjugate prior distribution in everything we do, we use MCMC to give us the shape. And then once we have the shape, we still do all the other stuff. We take its mean, we take its standard deviation, we figure out its range and so forth. So what we do with Stan, why we're using Stan for this is because there's no easy mathematical formula. I wouldn't say this is easy, but the mathematical formula is not closed, right, when we choose different priors or choose different models. And so, but this evaluation of the posterior will still continue. And at that, I'll stop there. Anything else before lunch? Or break, whatever.
Where should people find lunch? Mannheim people, can you help us out?